Thanks everyone so much for having me. I'm sorry that we can't all be in person together, but it's nice that I'm really glad that this week is continuing. This conference is continuing in spite of the coronavirus. So as on this first slide, I put the slides up on my webpage just in case that helps. So there are many ways of entering the same link, but I just sent it over chat so that you can kind of go forward and backwards at your own leisure. So I want to talk about, a couple things related to a recent result of mine with Justin Hilburn. It's a kind of analog of Tate's thesis in the setting of de Rham geometric Langlands. So part of the motivation from our work comes from a pretty large body of conjectures these days arising from, on the one hand, harmonic analysis for harmonic forms and also, certain dualities in mathematical physics. So these conjectures, they're new in the world of geometric Langlands, and a lot of them are, many of the conjectures in this area are conditional on very strong forms of geometric Langlands conjectures, and so they're kind of conjectures piled on top of conjectures. They're compatibilities for things that we don't know, and that makes them hard to reach. But what I want to talk about today is my work with Justin, which is sort of the first result in this hierarchy. It's only in the abelian case, and so everything's very explicit, and it's great because everything just works, and so the whole kind of body of conjecture seems more plausible because of that, and that's one of the I think nice outcomes of our work. So first test. So from the physics perspective, also our work provides a very strong version of 3D mirror symmetry conjectures. Again, a sort of baby case of them, but the results are quite a bit stronger than I think what's usually considered in the area, and so that's kind of cool too. So I want to begin with some motivation, and then I'll state our main results in the local setting. So then I'll talk about the connections with mathematical physics and with 3D mirror symmetry. Then I'll state some global versions. It's partially motivated by the mirror symmetry stuff, but also that's just going to be a little bit of an aside to break things up. And finally, I want to discuss some other applications joint with Braverman that are kind of applications to PGL2 that are a little fun. Okay, so attribution. So the circle of ideas that I'm discussing, 3D mirror symmetry and related topics, it's been developed by many people. So I'm not sure that I'm at all exhaustive here. So I'm sorry if I'm missing something or if I'm inaccurate about something, and especially if I'm leaving you out, you personally listening on the other end. So on the mathematical physics side, this kind of general subject we're talking about is 3D mirror symmetry and also its relationship with 4D S duality. So the former subject was started by Intriligator and Seiberg, and then developed by Hanani Witten and many other people starting, I think, in 96, 97. The connections with S duality, as far as I know, were first considered by Gaiotto and Witten, but I'm probably wrong about that. And the sharp mathematical conjectures that I'm discussing here were, as far as I know, first considered by Justin Hilburn and Phil-Sang Yu, maybe jointly with Dimoft and Gaiotto, and then Braverman and Finkelberg also developed these ideas further, and appreciate them. So I think the result I'm talking about today, I first heard as a conjecture from Braverman, who first heard it as a conjecture maybe from Justin and Phil-Sang. In harmonic analysis, this body of conjectures has like a totally different lineage and comes out of, especially work of Yannis Sekularidis and Akshay Venkatesh, that, their work is trying to provide a unified perspective on period expressions for L values. So recent work of theirs, joint also with David Benz-V, really kind of joins the perspectives of mathematical physics and harmonic analysis here and connects with the geometric Langlands program. And I thought, also their work really emphasizes global aspects of the subject more than I think, this sort of body of people coming out of the math physics world were considering. Although it's quite natural from the physics perspective as well. So then I want to put a disclaimer, which is that this is new work. Some parts of it are still in progress. The theorems I'm talking about here, they have complete proofs, but they're not totally written down yet. But also there's a number of interesting related questions that we haven't settled yet. So I'm going to try not to raise them, but people might. So to get started, so I'm going to work over a field K of characteristic 0. And I'm interested in geometric representation theory for the kind of non-Archimedean field, capital K, which is the Laurent series field over my ground field here. I'm going to take O always to be the subring of Taylor series. And yeah. So roughly speaking, what is Tate's thesis doing? Well, in the local setting, it provides a sort of detailed analysis of the spectral decomposition of functions on this ring of Laurent series under the natural action of invertible Laurent series, considered as a multiplicative group. So here, he's working over a finite field and so on, but whatever, or over a p-adic field. So the short, but standard analogies apply, and yeah. So the kind of short summary, that's a little bit trying to be detached from working in a particular context, is that for kind of non-trivial characters, well, I really should say for ramified characters, kind of nothing interesting happens. That character kind of extends canonically to the whole vector space of Laurent series as a function, and it generates the corresponding eigenspace. But something singular happens if you work around the trivial character or kind of an unramified character, a little bit depending on how you say things. And there are singularities in the harmonic analysis that give rise to poles of zeta functions. So I'm saying this because we'll see it in a little bit. So to imitate this in geometric representation theory, the standard thing to do is, instead of considering functions on K, working over a finite field, I consider the category of D modules on K in place of functions. So there's something to say about this, because usually categories of D modules, they refer to things in finite dimensions, whereas this sort of, if I think about this vector space of Laurent series, that's hugely infinite dimensional over my ground field. So some words of explanation is needed. So first, let me just define some kind of spaces. So if I'm given an affine scheme Y, then I define two spaces. So one is Y of O, and the other is Y of K. So Y of O is a scheme, and it has the property that mapping to it from some affine scheme is the same thing as a sort of map after I cross with the disk, cross my S with the disk in a suitable sense. So it's a kind of Taylor series, in a sense, worth of maps from A to Y. And same thing for Y of K. So that produces an ind scheme for me. And so a union of schemes. And it's the same thing, but with Laurent series replacing Taylor series. And yeah, I don't want to say too much about this, but the basic thing is that both of these guys are kind of well-behaved objects of algebraic geometry. For instance, if my Y was A1, this would sort of be O. I guess I'll write this in a second. Yeah. This would sort of be O, thought of as an algebraic geometric object, and Laurent coefficients or Taylor series coefficients would provide like coordinates on this infinite dimensional vector space. And same thing with Y of K and Laurent coefficients. The reason Y of K is an ind scheme instead of a scheme is because Laurent series by definition have bounded order of poles. So it's a union over the order of poles. So similarly for Y being GM, I might just write O cross or K cross instead, and just think about those as, again, algebra geometric objects. So the next thing is that, what are D modules on these kinds of spaces? So, I just said this. So I think about K as some kind of, let me just explain in the case of K where it's quite concrete. So I think about this as an affine space with these coordinates. And so what would a quasi-coherent sheaf on K be? Well, it should be a vector space V, and there should be certain operators AI coordinating to, I should have said commuting operators, AI corresponding to those different functions, like those functions of take the Laurent coefficient. And the basic property should be that every vector is annihilated by all functions AI for I sufficiently negative. And similarly, a D module, it's defined quite similarly. So it again has operators partial sub AI, so derivative in kind of that direction. And it should have the basic property that for every vector V, the kind of opposite condition holds. So, so these partial a sub I v's kill any vector for I sufficiently large. And again, these partial a sub i's should mutually commute with each other. And then I should also have this identity, the kind of usual Viol algebra relation. So such data, let me just say, are equivalent to modules over the Viol or beta gamma or CDO vertex algebra. So it will be familiar to some people in that kind of guise. And let me just also comment, although this isn't really going to be needed later, that the above definition also has there's a more categorical way that you can say things. So if I take D modules on K, one way to describe that is it's going to be the co-limit in a certain sense, the kind of union, but in a slightly non-obvious sense of categories of D modules that are sort of bounded on these subspaces, like D modules with support on these subspaces T to the minus n of O. And well, because this is infinite type, that deserves an expression also. So those things kind of by definition are, again, essentially the union of things pulled back from T to the minus n of O mod T to the m of O. So when I say essentially or non-obvious or something, the only thing is that I allow infinite direct sums of those things. So I don't literally mean that every D module has finite support or is pulled back. But basically what this means is that this formula says that D modules on K, they're just built out of finite dimensions via functoriality. And so that's a kind of convenient perspective sometimes. And this definition is really the one that's well behaved on derived categories. And so this is really what I have in mind as my definition of D of K. So similar reasoning lets me define D modules on the space on this K cross space, the space of invertible Laurent series. And it's a symmetric monoidal category under convolution, meaning using the group multiplication on K cross, I get a monoidal structure. And so this category acts canonically on my category D modules on K. So now the sort of local Tate's thesis problem is, in some sense, kind of quote unquote or whatever, to understand the spectral decomposition of this module for D of K cross. It's module D modules on K. And so in order for that to make sense, like what do I mean by understand, for instance? So in order for that to make sense, let me recall what's called local geometric class field theory. So this is a theorem of Beilinson and Drinfeld that says that there's a canonical equivalence of categories between D modules on K cross, so that monoidal category we considered before, and the category of quasi-coherent sheaves on locus GM. So first of all, locus GM, I mean the moduli of rank 1 local systems on the punctured disk. And by local system, I mean what's called de Rham local system. So those are line bundles, or if it were higher rank, they would be vector bundles with connection on the punctured disk. So I have that's the moduli space of a vector space over the field of Laurent series plus a connection. So let me say the kind of, there are versions of Riemann and Hilbert that work here, but these are finer objects than like local systems on a circle. So because of the existence of irregular singularities, this the space is more robust than you might think if you think topologically about it and haven't thought about these things before. So let me just say kind of by definition carefully what I mean by the space locus GM, just to be a little careful. So what I do is I take this group in scheme, this K cross, and it acts on KDT. So basically this in scheme K, but maybe with some kind of formal variable attached just for change of coordinates reasons. And the point is that I have a D log map sending a function f here to df over f, and then I can form the stack quotient. So this is a map from this multiplicative group to this additive group. And in particular, I get an action of K cross on KDT via it, and I can form the quotient, and that quotient is locus GM. Yeah, and I should say, by the way, the monoidal structure over here, this convolution structure goes to tensor product on the other side. And so you can sort of picture that a D of K cross module category, it sort of fibers over the space of de Rham, rank 1 de Rham local systems. And yeah, this theorem of Beilinson and Drinfeld, it's a consequence of Cantu-Ferrer's duality, and Justin Campbell is going to speak about that later this week. Some kind of new perspectives on that subject. So now let me define a certain space Y. So this is kind of with topologies. This is just the notation I'm using. And yeah, there's nothing evocative about the name. So I'm going to define Y as a moduli space of data consisting of a line bundle on the punctured disk, a connection, and a section. So this is my data of a line bundle with connection, as stated, so a point of locus GM. And then I also have a section that's annihilated by the connection, so a flat section. So another way a person, again, this will be appealing to some people and not to others, is you could say that this is the space of maps from the punctured disk to Rham to A1 mod GM. So, you know, this is kind of one way of thinking about it, and this is a little pithier. Okay, so at a technical level, so there's a sort of technical result about what Y looks like that maybe isn't going to be super meaningful to everyone, but I'll just still say it and then move on. It's a slide talk, so it goes fast. So Y can be expressed as a quotient of something. So what is it? So first, it's going to be an ind affine scheme. So it's again ind because I sort of have infinite orders of poles around. There's a quotient of some group. The point is basically you quotient by GM and you quotient by the affine Grossmannian for GM, and that's all you have to do. And the last thing is that it's classical, which means that a priori, I could have had a DG scheme. So if you know something about DG schemes, one thing you know is that they often come up when you form fiber products. When you impose equations, when you think about a variety just in terms of equations, if those equations aren't kind of defining a locally complete intersection or something like that, then it kind of often happens that it was better to have thought of your thing as a derived scheme for certain purposes. And there's something similar that happens here. I impose an equation here, nabla of S is equal to 0. And kind of in effect, what happens is, although the situation is very infinite dimensional, and you should be careful what you mean, that equation kind of turns out to define, it's sort of, it behaves like an LCI equation, like a locally complete intersection equation. So that was a sort of first happy result in this kind of test of, you know, this body of conjectures. You know, spaces like this often behave very badly, but kind of miraculously, this one doesn't. And so one consequence of this in particular is that I can make sense of ind-co of Y. So I'm not going to say a ton about that, but it's quite concrete, and yeah, we can talk about it in other settings if there's interest. But kind of a priori, let me just say this ind-co, it's kind of, there's something Noetherian-y about it, and this Y is quite
Sam,
something.
can I ask a question?
Sure.
Can you give an example of a space that sort of naively looks very similar to this one, but actually doesn't arise as a quotient of any classical ind scheme? Like, what?
Yeah, so there's two things, right? So there's, so there's kind of two things that can go wrong. So one is about like the stackiness. So the point is like this part kind of acts freely, so to say, this congruent subgroup. But if I replaced my A1 here with like BGA or something like that, I get a space that's like a beast. I don't know how to work with it for stacky reasons, not for like classical or derived reasons versus derived reasons, but it's just like that subgroup doesn't act freely at all, and you're in total trouble, kind of trying to approximate it by finite dimensional geometry or something like that. But yeah, I think if you take the maps from like a punctured disk to the dual numbers, I think something like that is already really bad.
Okay.
So, yeah.
Thanks.
But kind of typically mapping from the punctured disk into something that's not smooth is bad, and mapping from the punctured disk to Rham into something that's not like basically B of a reductive group wasn't previously known that it was at all good. So this is a kind of first case of that. Yeah, so our theorem now, our local theorem says that there's a canonical equivalence of categories between the two things I described. So on the one hand, D modules on K, and on the other hand, this category that exists, ind-co of Y. And this is compatible with local geometric class field theory in the sense that I have d of k cross acting on this side, and on the other hand, my space of and on the other hand, my space y maps down to the space of local systems on the punctured disk just by forgetting my flat section. And those two structures are compatible with the theorem of valence and Drinfeld. So that's the kind of key main result. Let me comment, this is really an equivalence of derived categories. So there's a natural T structure over here that I kind of indicated before, and it doesn't match to anything seemingly nice on the other side, which is unlike the result of valence and Drinfeld. That result is kind of naturally T exact. So let me just kind of make a couple remarks very quickly. So, so suppose I have some non-trivial local system with connection. So then it has no flat sections. If it had a flat section, if it had a non-zero flat section, that would automatically be an isomorphism with the trivial local system. So in this case, our result kind of matches the phenomena I highlighted earlier from Tate's thesis. So namely, like, so to say, nothing happens away from the trivial local system, but there are singularities over the trivial local system that are kind of finer functional analysis. But this is just like a kind of funny remark. So it's actually not true that if you try to say that in families, so if you try to say this in families as opposed to at field valued points, you get wrong statements. So if you try to base change y to this sort of space of non-trivial local systems, that map actually isn't an isomorphism for subtle reasons. So that's just a kind of funny thing for anyone who is amused by, who shares that particular sense of humor. Okay, so maybe now's a good time to pause for. Okay, so yeah, so now I kind of briefly want to talk about the relationship with mathematical physics things, and just kind of give some formalism a little bit for how to think about things. So what physicists will tell you is that we're talking about 3D mirror symmetry in this setting. So let me remind that 3D topological field theories, they're the kind of things that might assign numbers to closed 3 manifolds, vector spaces to 2 manifolds, and categories to 1 manifolds, closed always. And and they're not always so defined. You might get some things and you might not get other things. And yeah, so there is something like this that actually exists in algebraic geometry that's not somehow topological exactly, but a little bit, well, topological in a Rham sense. So this is a kind of outline of a definition. There is a real definition here, but it's not helpful to provide all the details. So let me say a 3D field theory Z on some smooth, proper algebraic curve X is, well, it's some data. So let me just give the flavor of the data and what kinds of structures we get. So the first thing is that anytime I have a point in my curve, there's an attached DG category, which is the sort of category that my theory attaches to a circle. So you think of that punctured disk at a point as being a 1 manifold, and I'm supposed to attach categories to 1 manifold, so here we are. Second, there should be certain morphisms coming from cobordisms. So the first one is that I can think about the formal disk as a cobordism from the empty set to a punctured disk. At least, who can stop me from thinking that way? And on the other hand, I can think about my curve minus a point as a kind of cobordism from the punctured disk to the empty set. Unlike the topological setting, the directions matter. So I have these directions, and yeah. So these cobordisms define morphisms. So the first amounts to defining an object in my category. So this is called the unit object or the vacuum object. And the second one defines a functor out of my category. So a functor to the category of vector spaces. And that, maybe I'll call it chiral homology. I don't have a good name for it, but that's one possibility. I can do various things. Did I write it? Yeah. So if I sort of compose these cobordisms, which amounts to evaluating this chiral homology on the vacuum object, I get a vector space. And that vector space is supposed to be the vector space that my 3D theory assigns to this, so to say, two-manifold X. Yeah, it's part of the axioms imply that that is independent of the choice of point X. The axioms I'm omitting here. But this is the flavor. So things that look like this, you get morphisms for, and otherwise follow your nose. So just as one kind of example of these things, so there's a large class of examples of this flavor. So if these words don't mean anything to you, don't worry. So if you're given a chiral algebra on your curve, then Bailenson and Drinfeld in their book Chiral Algebras defined, in effect, a 3D theory attached to this chiral algebra. So the first thing is, what's my category? So this is called the category of A module supported at a point. And the vacuum representation of A, which is the sort of fiber of my chiral algebra at the point, provides this favorite unit object. And Bailenson and Drinfeld also defined something called chiral homology. And this, it's exactly a functor like on this page. And so they do all the things you're supposed to do. So that's how I think about 3D field theories and algebraic geometry. You might think that somehow like algebraic geometry, how could it be three-dimensional? And kind of the answer is you stick one of those dimensions, make one of those dimensions kind of categorical in some sense. It's sort of, you might say it's like topological in a true sense. And that just has to do with like raising the level of categorical complexity. And it's related to the fact that my theory wasn't at all defined. I said 1, 2 extended. I only define it on 1 manifold and 2 manifolds and say nothing about 0 manifolds or 3 manifolds. Okay, so now for, so what's kind of the next thing we should know from physics? So the next thing is that for a stack Y, physicists will say that if you take so this is now something not algebraic, I don't really know what it means. Well, I don't know how to exactly pull algebraic geometry out of it, but it's a little bit of a heuristic. So they would say that the three-dimensional sigma model with target cotangent bundle of Y has what's called n=4 supersymmetry. And so practically what that allows us to do is to construct other theories out of this given theory. And so there are 2 twists. So those are other theories attached to a given quantum theory in the presence of supersymmetry. And those are themselves 3D theories, ZY sub A and ZY sub B. And the properties that, and those are going to be actual algebraic theories. This is, again, kind of heuristic. But the good thing is that because these are algebraic theories, I can just tell you what they are. So the basic properties here are that if I take this A twist and I take the category attached to a point, or the punctured disk around a point, it's going to be the category of D modules on that Y of K that I discussed earlier. And if I take this B twist, then it's going to be ind-co, let's say, on the space of maps from the punctured disk to Rham to Y. I think I wrote the base point here and didn't really write it otherwise. Well, maybe, okay. Everything is going to be based at this point, and that base point might disappear soon. So now there's something physicists call 3D mirror symmetry, or 3D homological mirror symmetry. So for a 3D n=4 theory, in the sense of physicists, what they would say is that there's a dual theory Z star, kind of a tautological dual theory Z star. So this theory is supposed to be the same 3D theory, but that n=4 part, those supersymmetries, are supposed to be realized in a different way. You basically conjugate the supersymmetry algebra and get a different realization of the same symmetries. There's a kind of outer automorphism you apply. So the main thing that happens there is that this A twist gets exchanged, like what we call the A twist for the theory Z is now called the B twist for the theory Z star, and vice versa. So now what mirror symmetry, actual mirror symmetry, refers to are having pairs Y1 and Y2, where the theory for Y1 is supposed to be the dual theory for Y2. So if we now take the previous slide, take these formulae for the A twist and the B twist, you get serious mathematical conjectures. So as one example of what's supposed to be a mirror dual pair, you can take Y1 to be A1 and Y2 to be A1 mod GM. And in this case, this prediction that the A twist for Y1 equals the B twist for Y2 amounts to this equivalence that I said earlier. If I were better, I would have flipped the sides, but Sorry. So this perspective with 3D theories, it suggests another kind of compatibility, however, if you think about the global setting. So suppose that I have this marked smooth projective curve like before with a fixed base point. So there's supposed to be this chiral homology functor from d of k to vect. And in fact, Beilinson and Drinfeld, well, all of the categories that appear here are at least close to categories coming from chiral algebras. And so you can open the textbook by Beilinson and Drinfeld and figure out what chiral homology is supposed to be in this case. And what they'll tell you is that you should do pull push, where here, this is this vector space of Laurent series. This is this vector space of rational functions on the affine curve obtained by puncturing at the point. And what I should do is pull back and take de Rham cohomology. And that'll be the chiral homology functor at this point. And similarly, the chiral homology functor for the space Y, it's given by thinking about Y as maps from punctured disk de Rham to A1 mod GM. And then I just do the same thing. Oops, I missed de Rham here, but there should be a de Rham right there. And then you push forward. So again, you pull back and then take sections. So a sort of refinement of our theorem is that actually our equivalence is compatible with these chiral homology functors, meaning if you take d modules on k, I just gave you a functor to vector spaces. If you take ind-co on y, I just gave you a functor to vector spaces, both of pull, push type. And the assertion is that these functors match under our equivalence. It's a non-trivial assertion. Well, it would be a trivial assertion if our equivalence came from an equivalence of chiral algebras, but it doesn't, and so there's something to prove. I would like it to be more tautological, but it seems not to be. So now, I see there's a lot of questions. Okay, maybe I'll refer back to them in a little while. The result I just said actually generalizes even further. So there are certain correspondences we can write down that are a little more robust. So the first is I can take this vector space of Laurent series again, and on the other hand, I can take, the space of maps from X to A1 mod GM. So these are line bundles with a section, and then I also trivialize my line bundle in a formal neighborhood of my marked point. And the space, by definition, certainly maps down to the space of line bundles with complete trivialization around that point X, around the marked point. And there's something similar I can do on the spectral side. So involving, just kind of the thing I get by puncturing at the point, and then this time I forget my A1 factor. And so these give rise, these two correspondences, again, by pull push, which, there are things to think about here about infinite dimensional aspects, but they, let me just say, they're kind of unique meanings for all of these things that reasonably make sense, and those unique meanings are the ones I'm ascribing. So these give rise to functors from, on the one hand, d modules on k to d modules on bun GM with level structure, and on the other hand, ind-co of y to ind-co on the space of local systems on the punctured curve. And now a refinement of our previous result is that actually these functors match under our equivalence and global ramified class field theory, which provides an equivalence like this. So it's easy to kind of deduce the previous results from this. So let me just say, like in the physics language, what we're saying is that our equivalence of sort of these 3D algebraic theories, it really upgrades to an equivalence of boundary conditions for the A and B twists of 4D n equals 4 super Yang-Mills for the group GM, compatibly with S-duality in the Sibelian case. And let me also comment that in the work of Benzvi, Sekleridis, and Venkatesh, results of these kinds are, they're the things that they maybe care most about. And these are their kinds of categorification of period identity. So this is a first check of their conjectures in this case. And at least like you can deduce the sort of conjectures they consider from the result I just said. Let me say, even though, so their result is purely like they're conjectures, you could say them purely globally. So here I had a marked point and so on, but you could say them purely in terms of the curve X and these kind of global chiral homology vector spaces or D-modules. And I don't actually know how to prove those without passing through this local story. Maybe it's possible, but I don't see it. So it's a slightly funny situation. And now I just want to mention some other applications that are joint with Sasha Braverman. So I'm going to write P1 bar just for fun to mean A2 mod GM. So if it were A2 minus 0 mod GM, it would be P1. But it's a sort of funny compactification, stacky compactification of P1. And so with Sasha, we showed that what are called Hecke D modules on the Grassmannian for PGL2. So by definition, this is something where you kind of, in a sense, trivialize, well, you take Hecke eigenobjects inside of D modules on the Grassmannian with respect to the geometric Satake theorem. So we showed that these are the same as D modules on this sort of compactified P1, like algebraic loops into that space, compatibly with PGL2 symmetries. And so from my work with Justin, actually, and some separate work of mine, we get a huge kind of massive equivalences that's kind of fun. So one is that if you take critical level Kac-Moody representations for SL2 and you fix the central character in a way I'll comment on in a second, this is so a certain kind of fixed central characters is what this means. So these are equivalent to so what I showed is that this is equivalent to this category of Hecke D modules on the Grassmannian. So Sasha and I show that this is also, yeah, I didn't write the renormalized here, but there's something to say about compact objects. So it's really renormalized D modules on this space. And Justin and I, well, one can deduce from our work that this is also equivalent to ind-co on the space of maps from the punctured disk to Rham to this P1. Just, sort of maps from the punctured disk to Rham to A2 would look an awful lot like our theorem, but then there's this mod GM and you can handle it. And so here chi is an operator on the formal disk, which basically means that I take my favorite formal disk and embed it into P1. So it's a PGL2 operator. Like that's the kind of structure that an operator is. So I make such a choice once and for all, and then I get an equivalence like this. And yeah, so that's what I've got. So thank you for letting me speak. Okay, so I can kind of go through the questions here really quickly. So yes, so Tony asked if there's a more interesting decategorification by taking trace of Frobenius, and absolutely there should be. So I kind of think, although I didn't so carefully check, that everything works for kind of crystalline things in characteristic P, crystalline D modules, and I think it might be possible to make sense of this trace of Frobenius. And yes, so it's an interesting question. And it's one of these things I haven't gotten a chance to kind of really.
But you can also, I mean, it's not very difficult, I think, to prove the Elatic version, but which will kind of poor one when you consider just very small categories. When you consider like sort of nilpotent singlet support on the constructible side, and on the coherent side, I guess, are the things which are over local systems concentrate at fine to many points.
Yes, that's absolutely true.
And this works in Elatic setting, and this I think is, I mean, I think I checked it a long time ago, and this is very easy to prove directly.
Yes, I agree. I think there's something more subtle going on. Well, there is something more subtle going on and more interesting and maybe more fun if you work with crystalline things, as you know well.
Yeah, but this I have. I mean, I'm sort of scared to even imagine this.
Yeah. Well. So. Yeah. So then, with a naive guess be wrong. Oh, okay. So that's just some discussion. Yeah. So. Okay. So Costello. Yeah. So there's this work of Gallardo, Costello-Gallardo, and Costello-Kreutzig-Gallardo, and they have, I think, constructions of parts of this equivalence via vertex algebras, via equivalences of vertex algebras, and that's not it's related, but our construction seems to be refining their construction. Like they only see kind of pieces of the category. They don't, for instance, look at like the whole beta gamma system. Can I say something about the braiding and the tensor product? So no, I think these categories are kind of too big to have braidings and tensor products. So it's like what I was saying about 3D theories. Not everything you want to be defined is defined. And yeah. Oh, but tutor ran. Okay, so that's the next message. So how does this level structure on the space of bundles look like? So if you trivialize a line bundle at a point, that's a GM torsor. If you trivialize it to order 2, that's a torsor for kind of GM times GA, like maps from your dual numbers kind of based at the point to GM, and you keep going. So it's some kind of pro gadget built out of higher and higher order level structures. And what is precisely the category for SL2? There are no finiteness conditions. So I take all modules, and it's not done by comparison with positive or negative level. It's done using, so the kind of comparison functor in the first place is given via the work of Beilinson and Drinfeld on critical level. So sort of the fact that these Hecke D modules, maybe with a slight twist, map canonically. Well, it's essentially a Beilinson-Bernstein localization theorem. So if you take global sections of a D module on Safran-Grassmannian, and then maybe let's say mod out by this central character requirement, there's a consequence of the work of Beilinson and Drinfeld is that this actually factors through this Hecke category in a canonical way. And so that gives you a functor. And my theorem says that it's an equivalence in this case of categories. Yeah, but again, all modules over this critical level Kac-Moody algebra with fixed central character. And the central character, again, it should be like, it should be something like a central character that would sort of support a baby vacuum representation or something like that. Could I say a word about how I prove this equivalence? Yeah, so I was really sorry when I finished my talk finished preparing my talk that I didn't have time to say something. So, so technically I have 4 minutes now, so I could say something in the next 4 minutes. Yeah.
No, Sam, I don't. You started at 2, right? So yes. You can go to 2. Oh, you can answer questions up until 3.
Yes. Okay. So Gayota's question is quick. The answer is yes. D modules on K are vertex modules for beta gamma. No, unfortunately, you can't give a similar interpretation of ind-co of Y. That's what's annoying. So the stackiness hurts you, and I don't see a way to do it. And yeah, and if you kind of try to think about it in terms of the beta gamma system, it's kind of, well, of course it's doable, but there are things on the beta gamma side that aren't so obvious somehow.
I was kind of hoping for something like a WCW model for GL1/1.
Yeah, I know from your paper, but it's not. Yeah, I don't know how to make that picture work somehow. Maybe we could talk some other time about it. I'd be glad. But yeah, so so I can say kind of very quickly for Drago or something. So so I can. So I'll give a construction of some Viol algebra somewhere, and then I'll try to explain what the relationship is. So this will be a Viol algebra that has something to do with the space Y. So let me give a quick kind of definition. So so this will be just sort of a regular singular version of what I'm saying. So I'll give a definition, which is some Z sub n. It's going to be the following kind of data. So I have a line bundle on the disk. Well, actually, maybe I'll even just be super canonical about it. So I have my line bundle with connection, which will have regular singularities, and therefore can be canonically put in the form O. O, and then, well, and then I should have a connection of the form D, I think minus is better, x over t dt. And then I have a function, and what the n will have to do with is that it should be in t to the n times Taylor series, and such that nabla, so this is my connection nabla. The basic property is going to be that this nabla of f is equal to 0. And then technically for stacky reasons, I should mod up by GM, but I kind of forget it. So this is a rigidified version of the space Y I was considering before. So all of this is kind of happening on a disk. So these are sort of Deligne style extensions of my line bundles with connection to the disk. And there's a claim, and yeah, so maybe let me take pi to map. Yeah, so what are the basic structures here? So I have, marker. Okay, I have this embedding of z, minus 1 into z0, or sorry, z1 into z0. So the number here has to do with again, the sort of order of 0 I require for my section compared to this extension to the disk. So these embeddings, and all of these map down to my space Y originally. So I can just take this F considered as a flat section on the punctured disk. And let me call all of these maps pi, just for laziness. And there's a claim, which is that in a suitable sense, if you take pi star of OZ0, or I should normalize this correctly, there's going to be an action actually of the Viol algebra on here. So I'll explain this. It's the flavor of the thing, and then maybe I'll have time to say what it is. So the first thing is that if I take this pi star of O sub z sub 0, this has a kind of restriction. Well, maybe if this map is like, well, this maps to the push forward of O z sub 1. So like kind of push forward along this embedding. Just by restriction. Yeah, you've got some closed, so you can form a restriction map. But now this pi star of O z sub 0 is isomorphic to like pi star of O z sub 1 on the other hand, just because all of these things, like, they differ from each other by a gauge transformation, like the action of t. So they, so all of these, from the perspective of Y, all of these fibered things are isomorphic. And yeah, so I have an isomorphism like this, but I also have a map in this direction. And so that gives me a map from pi star of O z sub 0 to this pi star I star of O z sub 1, which is equal to pi star of O z sub 0. And this restriction map is sort of my map T that I claim exists. There's a map, there's a slightly more fun map, which is that you can map O z sub 1 to O z sub 0. So this is the opposite direction now to what I just wrote down. And this map is given by multiplication by x, where x is the same coordinate that I wrote down here. So it's the sort of residue of my connection in this case. And yeah, and this really, again, goes from sort of the push forward of I z sub 1. And this is going to be my map dt. And there's an exercise that will then give you all of the main ideas for our work, which is that this map is well defined. So that's kind of fun. So, in principle, well, what you need to do is show like that this multiplication by x map, like this z sub 1 is some kind of closed in z sub 0. So it corresponds to an ideal sheaf on z sub 0. And you need to show that that multiplication by x annihilates that ideal sheaf for this map to be well defined. And so unwinding things, there's content to this statement. But then the basic thing is that sort of the reason that the Viol algebra relations are satisfied is very satisfying. So, so I had this map multiplication by t, which was just some restriction map. And then I have this map d sub t from here to here. But when I want to do a commutator, sort of on the one hand, I'll go from oz sub 0 to oz sub minus 1 by sort of translating this map d sub t, like translated. So I'll put tr to mean translated. And then I just restrict. Or I could have gone by restricting to oz sub 1 and then applying my d sub t from before. And so this is multiplication by x. But when you translate multiplication by x, it turns into multiplication by x to the plus or minus 1. And so the difference between these two things is a copy of the identity. And so that's where the Viol algebra relations come from in this case. So that's a kind of crash course on the flavor of this thing. And then maybe the last kind of comment about how what I just explained relates to the equivalence is that I have an evaluate, sorry, this thing takes a second to be usable. Well, I have a correspondence from A1 of O, space of Taylor series. So I can just evaluate at 0 to get a map down to A1, and this embeds into K. And so that gives me a functor from d modules on A1 to d modules on K. And that's essentially what I just constructed. My object with an action of the Viol algebra will be the image of differential operators under this functor and our equivalence between d modules. So this gives a map d modules on A1 to d modules on K, which is supposed to be equivalent to this ind-co on Y. And in effect, what I just wrote down is this functor. It's kind of the content. So yeah, it's kind of a long answer to Dragosh's question, but I think that exactly finishes up the time.
So I think we'll move to informal conversations now, but it will restart again in 15 minutes, so 15 minutes after the hour. And I saw that Dylan and David had questions, so maybe that can continue into the informal discussion.
Great.
Let's thank Sam again.